Hello everyone, today I want to explain my homework 6.2. Write a LD to control piston with dis- distribution ejection plant by running timer 10 seconds, counter 5 times, after that model on and show flow theme together. This presentation will, will follow this structure. First, an overview of the experiment, then the hardware and the photometric diagram used, followed by a detailed look at the lander diagram program. I will then explain the program and highlight key knowledge points, show the fault theme simulation results, and final conclude the report. The system consists of an Omron PLC as a counter, two piston cylinder for distribution and ejection, solar levers, limit switches for piston feedback, and timer, a counter, and a model. The control flow is straightforward. Up starting the piston move in sequence controls by the timer. The counter keeps track of these circles, and once it hits 5, the motor is turned on. The hardware used includes an Omron PLC, two double-acting piston cylinders, two 5x2 with solar levers to control airflow, 4 limit switches to detect piston positions, and the necessary cables and tamping. On the right is the photometric control diagram, which shows how the solar levels and the limit switches interact to control the movement of the distribution and injection position. Now let's look at the lander diagram program. This first section covers the internalization, including the start and result buttons in network 0. Network 4 handles the control for the first piston's action, and network 10 fetches the first timer T000000 set for 10 seconds, which controls the timing of the piston's extension or retraction. This part is critical for understanding how to use basic timer instructions in PLC programming. Moving on the second part of the LD program, network 21 has the second timer T000001, also set for 10 seconds, controlling the second piston. Network 23 is control logical. Most importantly, network 34 introduce the counter C000000, which is configured to count up to 5. This counter increments each time a full circle of piston movement is completed, demonstrating how to count repetitive actions in a PLC program. The third and final part of the LD program is where the model is active, as shown in network 38 and 41. The model outputs Q100.000 and Q100.01 are initialized only when the counter C00000 has finished counting 5 circles. This is a key part of the logic, showing how the PLC waiting for a specific condition. The counter reaching its set value before executing a final task, which is turning on the model in this case. To simulate the key knowledge from this experiment, we covered the fundamental of lambda diagram programming, including context and coils. We learned how to use the TRM instruction for time delays and the CNT instruction for counting events. The experiment also reinforced the concept of sequential control where machines follow a predefined step-by-step process, and the importance of interlock circuit for safety and correct operation. The overall logical is a classical example of how PLC are used in structure to automate repetitive tasks with specific timing and counting requirements. Before implementing the program on physical hardware, we used float-sum software to simulate the entire system. This involved creating a variety model of both the photometric circuit and the PLC lambda logic. The simulation successfully demonstrated that the pistons moved according to the timer setting. The counter actually counted 5 circles, and the model turned on as expert. This step is critical for validating the design and catching any errors before real-world testing. Let's look at the video. In conclusion, I successfully designed and implemented the required lambda diagram using a oblong PLC to control the piston system. The timer and counter functions worked as intended to create the sequential control logic, and the model activation was correctly targeted after 5 circles. The flow sim simulation was a valuable tool in verifying the system's operation. This experiment has significations improved my understanding of PLC programming, automatic systems, and the principle of industrial automation. That's it, all my homework 6.2. Thanks for your listening. See you.